Okay, so last time on the first part of this video, we left off and we had just derived our way through this wonderful function here, right? So we got all the way through to the end result. And again, just to recap, d of x comma t represents, right, the function of when we have our two waves of the same frequency or wavelength, but they're coming opposite directions. We do a little bit of trig, do a little bit of magic here, right? We end up with this resulting function. So again, the conclusion to walk away with is we end up with a function that kind of takes these two pieces and combines them together, right? So they define these separately, but we just saw that we had d of x comma t, and it equaled 2a sine of kx, and then cosine of omega t. So notice again, all they're doing is they're breaking this into two separate functions. And it kind of makes sense because this function looks a lot like what we would normally do for our displacement vector, right? So it looks a lot like what we would normally do for our displacement function for a particle on a wave, right? Whereas this function here, they're defining the amplitude as its own function based in terms of this, right? So the big thing to walk away with is to realize the amplitude, a of x, is going to depend on, obviously, the amplitude of each wave, but it's also going to depend on what position we're looking at, which makes sense because we're resulting in a standing wave, right? So as I do this, we're forming a standing wave, and we know that a standing wave has amplitudes, so it has antinodes and nodes. And again, the nodes are where the amplitude should be 0, whereas the antinodes are where the amplitude should be at a maximum, right? Now, if we're being specific, the antinodes at a maximum value here should be twice the amplitude of either wave individually, because if I had two waves and they were constructively interfering, the amplitude there should be 2a. Well, this function makes sense for that, right? Because at some values for x, at certain values for x, sine would be 0, and therefore the entire amplitude function would be 0. That would relate to the nodes. And for some values of x, sine would be 1, which would give me 2 times a times 1, which means at some certain positions I have a maximum amplitude. And then I have anywhere in between, right? I could have anywhere from 0 to an amplitude of 2a. So like if I just chose a random point here, if I choose to look at this point right here, that point is going to oscillate between these two positions. So if I wanted to find the amplitude of that particular point, I would simply use this function, and I would need to plug in what's the horizontal distance for that position, for that point, and then I would be able to find out what's the resulting amplitude of that function. Now, if I wanted to find out specifically where that point is at a given time, that's when I would use this part of the function as well. So the function has two benefits for us, right? It helps us find out basically where the antinodes and the nodes are, and it also helps us find out exactly where the particle would be in that process of the antinodes and the nodes. Okay, so again, let's just kind of break this down and break it up a little bit more. So how can we use the amplitude part of our function, the amplitude part being just that first part out front, much like we've seen before, right? So compare this to how we would normally say a cosine of omega t, right? So this portion here is representing the amplitude. So the amplitude function here. So how can I use 2a sine of kx to find the location of the nodes? Well, if this represents my amplitude, we already know by definition what the amplitude of the node should be, right? The node should happen where the resulting amplitude is always 0. So the nodes happen at any location where the resulting amplitude is 0. So we know we want our amplitude to be 0. So in other words, I can take that and plug that in. I got 0 equals 2a times sine of kx. Right. And then from there, I can simply try to rearrange this and kind of solve for a generic function. Right. So obviously, if I want to, I could divide both sides by 2a. That's pretty easy, pretty painless. Right. So 0 divided by 2a is still 0. So we end up with sine of kx equals 0. Now keep in mind, k is the same k we've seen before. So k is really equal to our wave number, which is 2 pi divided by the wavelength. So I'm going to go ahead and substitute that in. So I've got sine of 2 pi divided by the wavelength times x, and then sine of that whole function equals 0. So then if I'm trying to solve for a function here for x to find my position, because I'm trying to find the location, so I'm trying to find my actual x values. So if I try to solve this equation for x, I'm going to do sine inverse of both sides. Well, if we do sine inverse of 0, keep in mind there's actually an infinite number of points, right, on the unit circle where the sine value is 0. So the sine value, the y value is 0 at 0, but it's also 0 at pi and 2 pi and 3 pi and 4 pi, right? So if I do sine inverse of 0, obviously on the left-hand side over here it cancels out. It leaves me with 2 pi over the wavelength times x. And then on the right-hand side, it leaves me with a set of points. So it could be 0, it could be pi, it could be 2 pi, it could be 3 pi. So generically, I would simply write the right-hand side of this as it could be m times pi for any integer m such that m is 0, 1, 2, right? For any integer or 0, then I could use that for m. Okay, so hopefully this is making sense so far because, right, those are the values that we could have for our pi and for our sine inverse of 0. So at this point we have 2 pi over the wavelength times x equals m times pi. Again, keep in mind our goal is we're trying to solve for the position. So I'm trying to solve for x. So if I rearrange to solve for x, then I get m times pi, and then I'm dividing by 2 pi lambda. So in other words, I'm dividing by 2 pi, but I'm multiplying by lambda. And if I clean that up a little bit, what that shows me is pi's cancel out. I get m over 2 times lambda. Or if I want to make that just simply m lambda over 2. Now, what we just proved, the nodes would happen at any integer multiple of half of the wavelength. Now again, think about what that's actually saying. So the nodes where we get 0 resulting amplitude, so the amplitude is 0 at any of these positions. Basically what we just proved was we mathematically proved what we already know. So I know some of you right now are thinking, man, that was exciting, right? I just mathematically proved what we already know. Because think about a wave here. So if I have a standing wave, if I have a string, going back to last year, we know that a string has to start and end at an antinode. So if I had the first harmonic, that's where I go from, and I'm sorry, I misspoke, has to start and end at a node. So if I have the first harmonic, remember that that is a half of a wavelength right there. So that makes sense based on this equation, right? Where would the nodes be? Well, in this case, they are 1/2 of the wavelength apart. So that would be as if I plugged in a 1 for m. That fits with the equation. Well, what if I don't have the first harmonic? What if I have the second harmonic, right? So the second harmonic is when I get a full wavelength from node to node. So something more or less like that. Here's my second standing wave, right? Well, look here. I started a node. The second node still acts at half of the wavelength. The next node over here happens at 2/2 or a full wavelength, right? Once again, they're increasing in multiples of 1/2, which is what our equation is showing us. So x equals, it could be 1/2, or I could plug in 2, right? If I did m equals 2, I could do x equals 2/2, or I could keep going, right? And sure enough, if I did just a random standing wave, right? So pretend that's a better picture, but it'll serve its purpose, right? If I do a random standing wave here, this node, that's a terrible node. This one's not very good either, right? But each of these nodes end up half of a wavelength, half of a wavelength, half of a wavelength. They all end up half of a wavelength apart. Okay, so again, as exciting as this is, and I know that it is just absolutely enthralling here, but, right, the idea is we just mathematically proved why the nodes happen where they do. So we've known this already, right? But we just proved it mathematically because of this function. Now, obviously, I'm not showing you this function just so we can do that, right? This function does have benefits because, again, what if I asked you where's the amplitude, half of the original amplitude? So what if I told you the amplitude of each wave was 2, right? So the amplitude of each wave is 2 meters. Well, we know right now the maximum resulting amplitude from that. So if the two waves constructively interfered, it would be 2 plus 2, which would be 4. we know right now the minimum resulting amplitude would be at a node, which would be 0, right? But what if I asked you anywhere in between? What if I said, what horizontal position do we have to have for the amplitude to be, right? So just what random position do I want the amplitude to be 3 meters? Well, this function is what allows me to find that. So this function does have a lot of merit, right? I use the easy case right now just to prove, right, what we already know. But again, it has a lot of merit, a lot of purpose beyond that. Okay, so we'll work with this a little bit more. So again, here's what I'm going to do with the examples. So here's the first example. I will have a rubric for this. And what I think I want to do is when you guys come to class next and Friday, I will have you guys kind of work through these, and then you can check my rubric for it. So I'm going to go ahead and move past this example for a moment, but this example will help us kind of again apply what we just saw. Okay, but I'm going to go ahead and wrap out just a couple minutes here, right? And I'll wrap out kind of the last couple key concepts that we need to focus on in this section. So when a wave encounters a new medium or a new boundary, right? So there's two different terms they sometimes call it. They sometimes call that a discontinuity, which would simply be a break in the medium. So it's when I encounter a new medium, so it's a break in the medium, right? Means a little bit different from our calculus terms for discontinuities. And then a boundary, obviously, is again just the boundary between two medium. Well, we know that two things happen, right? When a wave encounters a new medium, some of the energy is transmitted on, and some of the energy is reflected back, right? Again, a discontinuity is just simply any change in medium, and a boundary is any time that there's this transmission, right? Or there's this reflection back. Okay? And actually they're defining here, they're defining that the boundary is when the wave only reflects back. So discontinuity is when both of the transmission and the reflection happens, whereas a boundary is when it only reflects backwards. So notice in our diagrams here, they're showing us that in this first scenario, the medium is changing, right? We're going from a thicker string to a thinner string. And as that happens, the medium does change. However, this would simply be a discontinuity because some of the wave reflects backwards while some of the wave passes forward, right? Whereas when I'm going in the other scenario, right, I'm going from the thinner string to the thicker string. Same thing happens, right? It's still a discontinuity. Some of the wave reflects backwards, some of the wave passes forward. In option C, or in diagram C over here, they show us a boundary where the entire wave reflects backwards. Okay, so notice the difference between diagrams A and B, right? What's the only difference here? So the difference between those two is that for A, we're going from the thicker string to the thinner string, whereas for B, we're going from the thinner to the thicker, right? So notice if we were thinking about the velocity for a wave, let's assume that the tension for each of those strings is the same. So if I'm thinking about the velocity of the wave, if the string is heavier, if the string itself is heavier, then the mass would increase. And if everything else stays the same, then that means that the velocity would decrease. So that's why they're saying that the speed here decreases. Whereas originally, if the string gets lighter, the speed would increase. Notice that when the wave passes from a low velocity to a high velocity, the wave stays upright as it transmits on into the new medium and as it reflects backwards, right? Notice, however, when I go from a high velocity to a lower velocity, when the wave transmits on, it still stays upright. However, when it reflects backwards, it is inverted. That is one thing to take notice of here, right, as we're looking at this diagram. Okay, so that's what we're looking at with the boundaries as it reflects. So again, couple notes, they're in your homework, or they're in your, your notes online for you. But if the wave speed is higher in the new medium, the wave pulse will maintain the same orientation, meaning it stays upright as the original pulse. So that's talking about the one that is reflected backwards, right? So if the wave speed decreases in the new medium, the reflected pulse will invert, as well as obviously decrease a little bit as well. And then because there's no transfer of energy when the wave reflects from a boundary, because none of the energy is passing through, the amplitude would remain constant.